Okay, testing. Okay, so hello everyone, welcome back to exercise class 9. I'm Adam. So in today's exercise class, I will talk about the solution of midterm. So let's start. First of all, let's go to the first question of the midterm. In question 1, oops. In question 1A, you're asked to reduce the partial differential equation of 2D Laplace equation into two ordinary differential equations and one separate condition using separation of variable. Okay, so let me write down the 2D Laplace equation first. Okay, we have the Laplacian of phi, which is the second partial derivative of phi with respect to x plus the second partial derivative with respect to y equals to 0. So first of all, separation of variable. I assume all of you should already know, should be familiar with separation of variable. So basically, what we do is letting the function phi as a function of x and y equals to the product of two functions, big X and big Y, which are which the big X, the function big X is the function of X only, and the big Y is the function of Y only. And by writing that and substituting these two functions into the equation, we obtain this equation where the x double prime means the second derivative with respect to x, and the y double prime means the second derivative with respect to y. And then we divide the whole equation by xy. Then we can obtain this equation. And then we can move x double prime over x into to the right hand side. And obtain this equation. Okay, now let's take a look. So for the left hand side, y double prime over y, since y is a function of y only, so we know that left hand side depends on y only. However, for the right hand side, x double prime over x, it clearly depends on x only. So for left hand side equals to right hand side, the only possible way to do it is for both left hand side and right hand side equals to a constant alpha. Okay, so here alpha is a constant. Okay, so therefore we can write the PDE, the 2D Laplace equation, into two ordinary differential equations. The first one contains the function x only, and the second one contains the function y only, and alpha is a constant. Okay, so that's the solution of 1A. And 1B, what you are asked to do is to further solve this equation and find the most general form of the 2D Laplace equation. And notice that in 1B, you're asked to find the most general solution. So you shouldn't put any boundary condition in this equation. So the most general form. Okay. So let's start with what we have finished last question, the two ordinary the two ordinary differential equation. And since we cannot impose any condition on these two equations or on the constant alpha, so alpha can be a positive number, a negative number, or even 0. So there are in total 3 cases you should consider. So for the first case, alpha is a positive number, so we can write alpha as a square number, let's say gamma square. Okay, so we can rewrite the two equations as follows. Again, gamma is constant, is a constant. Okay, and these two equations, these two ODEs are very easy to solve, and I can just write down the form here. So for the first equation, the solution are simply a sine and cosine function. And for the second equation, the solution is simply exponential function. It's exponential of gamma y and minus gamma y. Okay, so by combining two solutions together, we obtain the product of x and y, which is simply product of sine cosine function and exponential function. Okay, so that's the solution of the first case. Alpha is a positive number. So for the second case, how about alpha being a negative number? So let alpha be a minus of a square number, minus beta square. Again, beta is a constant. Oops. Okay. So again, by substituting alpha equal to minus beta square, we can obtain the same two equation. But this time, instead of plus gamma square on the first equation, we have minus beta square in the first equation. So the solution of two equations just basically swapped. So right now we have the solution of exponential in the function of x and sine cosine in the function y. So again, by combining the two solutions together, we can obtain this form. Oops. Okay, so that's the solution of the second case. For the last case, alpha equals to 0. So we simply have x double dot x prime prime equal to 0 and y prime prime equals to 0. And the solution is very easy to obtain. So just basically for x, we have a linear function of x, And for y, we have a linear function of y. So again, by combining both solutions, we obtain this form. Okay, now to write down the most general solution, we have to combine the solution of the previous 3 cases. So we have to do a linear combination. So for the general solution, phi xy equals, so first let's write down alpha equal to 0, we have both x and y being a linear function. So that's the first case. That's actually the third case. Okay, and for the first case, just too light. Okay, we have sine and cosine of x. So let me write this down. Sine and cosine of x, and for y is the exponential function. And one thing you should notice that since although in this case alpha is a positive number, but we don't know what exactly what's the condition of alpha. So we don't know what particular positive number it should be. So for the case of the most general solution, all possible positive number could be the solution. So instead of having one values of gamma, we may have multiple or a lot of possible values of gamma, any possible values of gamma. So we are summing all possible values of gamma m. So we have to add a summation sign here, summing all positive eigenvalues. And the same goes to the negative value alpha. So for x is exponential, and for y is sine and cosine. And again, we're summing over all possible eigenvalue beta n. Okay, so that's the full form of the most general solution of 2D Laplace equation. Okay, next question, 1C. So for the next question, 1C, we now have an infinite plane located at y equals to 0, and we have the static charge density sigma being equals to sigma naught. And the static charge density is a function of x being sigma naught cosine kx. So, and this plane is located at y equals to 0. So the very first thing for solving the Laplace equation is to write down the boundary condition. So first of all, for boundary condition, the derivative of the difference of the derivative of the potential, the electric potential, is equal to minus sigma over epsilon naught. So that's the first boundary condition. You should all remember. So basically, it's just the E field above minus the E field below equals proportional to the surface charge density. And in this case, in our case, the direction normal to the plane is the y-axis. So we have the partial derivative with respect to y. And for the above case, it's actually y equals to 0 plus. And we have to minus the derivative of phi, partial derivative of phi with respect to y again. And we calculate the value at y equals to 0 minus right below the plane, equals to the surface charge density over sigma, over epsilon naught. And in our case, the sigma equals to sigma naught cosine kx over epsilon naught. And by looking at the right-hand side alone, we find that because in the right-hand side, we only have cosine kx. So the x term of the potential phi can only contain the cosine function. Okay. So if we take a look at the solution in 1b, we are referring to this case, the x term containing only the cosine function. So right now, we can write down the form of the potential. So for y greater than 0, so for potential above the plane, we have this form, cosine kx. But because by comparing to the solution of 1b, cosine kx in the boundary condition of our in the right side of our boundary condition, the value k matches the eigenvalue cosine gamma x. So in that case, we know that there is only one possible eigenvalue, gamma equals to k. And for the y term, it's just exponential. So we have exponential ky and exponential of minus ky. And similarly, for the potential up below, right, we have a similar form. So for the x term, we're containing only the term kx. So right now, what we have to do is to find out the coefficient of A, B, C, D using other boundary condition. So the second condition you can use is that for y goes to plus or minus infinity, so for the potential very far away, the potential does not diverge, so the potential goes to 0. And in that case, you can drop the coefficient A and D. So because for right y greater than 0, exponential ky will diverge. So for the first case, a triple equals to 0. And for the second case, for negative y, for when y goes to negative infinity, exponential of negative ky will diverge. So again, d should equals to 0. So by putting these two equations to be 0, we can further reduce the potential, the form of potential, to these two forms. Okay, so for potential above, we have exponential minus ky, and for potential below, we have exponential ky. And for the third condition, boundary condition, we can use the continuity condition, which is the potential above equals to potential below. So this is the continuity equation, continuity condition of the potential. And what it does is clearly putting B equals to C. So now combining all the results, we only have one parameter left, one coefficient left. Let's put it as phi naught. And we can combine the case for y greater than 0 and y less than 0. So we have exponential of minus k times the absolute value of y, and then multiplied by cosine kx. So this form combined the two cases, y greater than 0 and y less than 0. And in order to find the value of phi naught, the only unknown for this equation, we can use the first boundary condition, which is I can write it again. The derivative of the potential above and below, and the difference is equal to minus epsilon naught cosine kx over minus sigma naught cosine kx over epsilon naught. So previously what we use is only the term cosine kx. But now, if we substitute the potential we found so far, we can obtain this equation. We can evaluate the derivative on the left-hand side in terms of phi naught. And the right-hand side is the same. And now we can find the value of phi naught in terms of sigma naught, epsilon naught, and k. So the value of phi naught is sigma naught over 2k epsilon naught. So therefore, the solution of this 2D Laplace equation is this. Okay. So that's the solution of question 1C. For 1 dot, finding the E field from the potential, so it is very easy. It's just basically taking the divergence of phi and then add the negative sign. So here I will just write down the solution, and I think you all can do the calculation yourself. So SGN here is the sign of y, because we have to take the derivative, partial derivative of y, and we have absolute value of y in our potential. So that's the solution of 1D. Okay, so next question, 1E. So now instead of a plane of static surface charge, we now have a plane of steady surface current K, which is equal to z hat K naught cosine Kx. So you are asked to find the vector potential for this configuration. So if you look at the form of the surface current density, it is actually very similar to the question 1C, because the form is basically a constant multiplied by cosine Kx. So supposedly you can just directly use the solution of 1C. So before that, let me write down the vector Laplace equation for vector potential A. So we have this equation, and if we take a look at the boundary condition, again, we have the partial derivative of A with respect to y in the case of both above and below the planes. And then we take the difference should be equals to minus mu naught K. And in our case, the K is K naught cosine KT z hat. Okay, so notice that the right hand side, first of all, is a vector, and it only contains z component, which means that the vector potential is only contains z component as well, because there is no x or y component on the right hand side. Also, if we replace it, the value sigma naught over epsilon naught in question 1C by mu naught K naught, then the boundary condition is basically the same as the boundary condition of question 1C. So we can just replacing epsilon naught, sigma naught over epsilon naught to mu naught K naught in question 1C. So you can just write down the solution like this. Okay, let me write it in a better form. Over 2K. Okay, so that's the solution of 1E. And for 1F, finding the magnetic field again. Magnetic field, the B field is just the curl of the vector potential. So I assume of you know how to perform the calculation of taking curl. So here I just write down the answer for you, and you all should be able to do it yourself. Okay, so that's the solution of 1F. Okay, so let's move on to question 2. So for question 2A, you are asked to perform the multiple expansion on the potential. So the general form of the potential is given. It's basically integrating, basically we have a charge distribution rho, and then we are integrating all the contribution. So let me draw a figure here. So in the particular coordinate, here, origin here, we have some sort of charge here with some charge distribution rho as a function of r prime. So we would like to find out the potential of an observer at a distance r. So what we basically do is integrating all the contribution of rho. So integrating r over r prime, r prime here. Okay, so the integrated form is basically Coulomb's law, because we are summing over rho over eta squared. So we define the distance between the observer and the charge density rho to be eta. So eta is basically the vector r minus r prime. And we integrating all the contribution, then we can obtain the potential. And here I define the angle alpha. Angle alpha be the intercepting angle between r and r prime. Okay, so first of all, let's expand eta in terms of r prime and alpha. So eta square is the distance is the square of the magnitude of vector r minus r prime. And using Coulomb law, we can obtain this form. And then by factoring out r square, we can obtain something like this. So r square multiplied by a bunch of things. So basically 1 plus something. So let me call it 1 plus epsilon. So here, epsilon equals to the ratio r prime over r multiplied by r prime over r minus 2 cosine alpha. And but in doing the multiple expansion, we assume the observer is much far away from r prime, which is the length scale of the charge distribution. So in this approximation, that means epsilon is much smaller than 1. So here we can take approximate the values of 1 over eta. So here 1 over eta is taking the inverse and then the square root of the previous result. We have 1 plus epsilon to the power of minus 1 over 2. Then we can take the Taylor expansion, and we keeping the leading order as well as the order of r prime over r. So for the order r prime square over r square, we basically just ignore it and treat it as the higher order term. So now we can plot this expression into the potential, the integrated form. So because we know what 1 over eta is, we can basically put this expansion here. So what we have is the charge distribution multiplied by 1 over r times 1 plus r prime cosine alpha over r, and then all the higher order term. Okay, and then we do an expansion separating those into two terms. So for the first term, we have 1 over r times 1. So basically just 1 over r. And since we are integrating over r prime, 1 over r is constant to this integral, so we can move 1 over r outside the integral. And what we left is just integrating all the charge distribution. And for the second term, we have 1 over r multiplied by r prime cosine alpha over r. Again, 1 over r term is constant to the integration, so we can move it out of the integration. And what we left in the integram is just rho times r prime times cosine alpha, and of course all the higher order term. Okay, so let me just copy the first term, and cosine alpha, r prime cosine alpha is equal to the vector r prime, because alpha is the angle between r prime and r. So r prime cosine alpha is equal to the vector r prime, the dot product of the vector r prime and r hat. And again, r hat is constant to the integration, so we can move r hat outside the integration. And remember, r hat is a vector, and the integration, the outcome of the integration is also a vector because we have the vector r prime inside the integration. So you shouldn't miss the dot product between the integration and the r hat. Okay. And then now the first term, integrating over all the charge distribution, is basically the net charge. So that's the monopole moment. And integrating the charge density multiplied by r prime. This term, the higher the term, is basically the dipole moment, P. So now we can simplify this form into this. So we have the leading order term, 1 over r, as the contribution of monopole moment, and the next term is the contribution of the dipole moment, which is 1 over r square term, and then all the higher order contribution. Okay, so that's the solution of question 2A. Okay. So for question 2B, here we have a hollow conductor, a hollow spherical conductor. and okay, also granted. So like this. So and then we have a dipole P outside the conductor, and then you are asked to find the potential of all space over the whole space, the potential phi over the whole space. And in this question, we are using the method of image charge. So let's just go a quick recap of the image charge method. So let's focus on the graph on the right hand side. So for the case of spherical hollow conductor, okay, grounded spherical hollow conductor, and if we put a charge Q at a distance d outside the sphere conductor, and for, by using the image charge method, we can put another image charge Q prime inside the conductor. So the Q prime has having the value minus R over D times Q. So where R, the big R is the radius of the conductor, and then the distance A, which is the distance of the image charge, equals to R squared over D. So by putting this image charge inside the conductor, we can obtain the solution that the potential on the sphere is equal to 0. So for the whole sphere, the whole surface of the sphere, the potential is equal to 0 by considering just the charge Q and then the image charge Q prime. So in that case, we can find the potential outside the whole sphere. And to obtain these results, I think you all have already did the calculation in problems. Oh, I forgot which problem set, but I'm definitely sure that you guys have did the exercise in homework. So if you forgot how to derive the image charge in this case, so please refer to the solution of the homework. However, in our case, we are not dealing with single charge Q. We are dealing with dipole moment P, especially in question 2b. We are dealing with a dipole which is I guess it's perpendicular to the distance. Okay, so perpendicular to the direction from P to the center of the sphere. So how do we perform image charge method in this kind of configuration? So first of all, we have to treat the dipole moment as two separate charge. So P, we let P equals to QH, where we have two charges plus Q and minus Q here, separated by a distance h, and then the whole charge Q and minus Q at the center of these two charges having a distance d from the center of the sphere. Okay, so by image charge method, we can put two image charge Q prime M plus Q prime. Okay, so in the color green, so the image charge above is induced by the charge plus Q, and the image charge below, the minus Q prime, is induced by the image by the charge minus Q. Okay, so we have, so this one is the dipole moment. And then we have the two induced image charge. So Q prime equals to minus R over the distance between plus Q and the center of the sphere. And since right now we are dealing with two charges, and the two charges are separated by the distance h, so the distance between plus Q and the center of the sphere is not exactly d. And by using Pythagoras theorem, it should be the square root of d squared plus h squared over 4. So we have this, and then multiplied by Q. So this is the values of the image charge. Again, similarly, for minus Q prime, we just invert the sign and obtain this similar result. And for the position of the image charge, R prime, again, we can use the image charge method, A equals to R squared over D. And similarly, in our case, R prime equals to R squared over square root of D squared plus H squared over 4. Okay. So it is quite obvious that the two image charge also form a dipole, because we have Q prime above and minus Q prime below. But one thing you should notice that not only the magnitude of the charge changes, the image charge have another scaling factor, R over square root of D squared plus H squared over 4. Also, the distance between two charges, the Q prime and minus Q prime, is not H. It also changes. So we should also consider the value of H prime. So by similar triangle, H prime over H equals to R prime over the distance between Q and the center of the sphere. So we now have H prime equals to R squared over D squared plus H squared over 4 times H, which is roughly R squared over D squared H if we consider very small h. Because if we go to the limit case, considering the ideal dipole, we should consider a very, very small h. So therefore, and similarly for the image charge Q prime, this is roughly equal to R over D Q when h close to 0. Okay, so therefore, we can treat the two image charge as the image dipole P prime, which is equals to H times Q prime. So for Q prime, so first of all for H, we have R squared over D squared H multiplied by the Q prime. And for the Q prime, we have an extra factor of R over D, Q, and also a minus sign here. So as a result, the image dipole moment is equal to R cube over D cube times Q times P, the original dipole moment, with an extra minus sign. So these two dipole moments are anti-parallel. So if I draw the arrow indicating the direction of the dipole moment, it should be pointing down. Okay. So, and also the distance of the dipole moment, the image dipole moment between the image dipole moment and the center of the sphere d prime is just r prime taking the limit h tends to 0. So it's basically r squared over d. So right now we can write down the potential. So for r greater than big R, which is the considering the potential outside the sphere, we have, so since there is no monopole moment contribution, we are only considering the dipole moment contribution. So we have P dot R hat. The R hat here should be the distance between the dipole moment and the observer. So it should be R minus D n hat. N hat is the direct the unit vector pointing from the center of the sphere to the dipole. So since we are writing the potential, so for this term, the potential from 2A, the contribution should be P dot R hat over R squared. But here we are using R, we are not using R hat, but we are using the vector R. So we are the form should be P dot R over R cubed. So for the denominator, we have R minus dn hat, and take the cube of the magnitude. So that's the contribution of the original dipole. And for the contribution of the image dipole, the form is similar. We have P prime times R minus D prime and hat, because this time the image dipole is located at D prime. Again, over distance cube. Okay. And then by expanding all the form, P prime is equal to minus P times R over D cube. And D prime is equal to R squared over D n hat over, again, R squared over D. And don't forget, for the potential inside the sphere, we have 0, because image charge only apply to the because we are only using image charge to the region outside the sphere. And for the potential inside the sphere, it should be 0, because all the surface, the potential on the surface of the sphere is 0. So potential inside is basically 0. For question 2C, this time the direction of the dipole is parallel to the direction of the distance between the dipole and the center of the sphere. So, and the dipole is pointing towards the center of the sphere. So we have plus q and minus q here. And again, we consider two image charge Q prime and Q prime prime here. And notice that at this time, the two charge plus and minus Q are having two different distance from the origin because they are separated by the distance h. So the induced image charge Q prime and Q prime prime may not have the same magnitude. So let me write it down first. For Q prime is equal to R over D minus H squared over Q, because for plus Q, the distance between plus Q and the center of the sphere is D minus H over 2. And the corresponding distance of the image charge is R squared over D minus H over 2. And for Q prime prime, we have the similar form, but this time it is D plus H over 2. Again, D plus H over 2. And you can notice that the net charge of the image charge, the sum of Q prime and Q prime prime are not zero. They are not having the same magnitude. So we should consider this time whether we have any net image charge. Let's put it as big Q prime. So big Q prime is the sum of all the image charge Q prime and Q prime prime, and also taking the limit out goes to 0 because in our case the dipole is actually an ideal dipole. So H goes to 0. So we have to calculate the difference of these two fractions. And then after some step, you can obtain this form, and Q times H is the dipole moment Q. So what we have is minus RP, sorry, dipole moment P. RP over D squared minus H squared over 4. And then taking the limit, we have minus RP over D squared. So we have non-zero net image charge this time. And for the image dipole moment, the form is quite similar. The setup is quite similar as well. So we considered the charge Q prime multiplied by the distance between Q prime and Q prime prime. So R prime, R prime minus R prime prime. So again, you just have to substitute all the H, R, D, and Q into this expression, and then taking the limit, QH over D squared minus H squared over 4. And then again, Q multiplied by H is the dipole moment P. So now we have, after taking the limit, R cubed over D times P over D squared. So basically, we obtain similar values of the dipole moment, the same magnitude of image dipole moment as the previous question, but this time we don't have the negative sign. So the image dipole moment is parallel to the dipole outside the sphere. So if I have to draw a vector to indicate the direction of the dipole moment, it should be like this. So they are parallel. And also the distance of the image charge or image dipole is well, you just have to take R prime and take the limit h tends to 0, and it is equal to R squared over D. So this time we can write down the potential just like before. So the first term is the contribution of the dipole outside the sphere. So we have similar form. And the next contribution is the image dipole, D prime and hat. And don't forget, for 2C, we have an extra contribution from the image monopole, big Q prime. Okay, so after plugging in all the thing, we have so let me write it down of the cube. So the magnitude of the image monopole moment over R. Okay, so that's the potential outside the sphere. And of course, don't forget, for the potential inside the sphere is always 0. Okay, so that's the solution of 2C. Okay, finally, for the last question for 2D. So this time we are considering arbitrary dipole moment. So dipole moment in any direction. So we can decompose this dipole moment into two components. The first one, Py, is perpendicular to the direction, to the distance from the dipole moment to the center of the sphere, and Px is the distance of the dipole moment parallel to the sphere. Okay. So we have the angle theta here. So that, and in this case, the unit vector of the distance between the dipole moment and the center of the sphere to be the x direction, and the perpendicular component be the y direction, and we can decompose the dipole moment into two components, the x component and the y component. And clearly, for the x component, the parallel case is you just have to apply the solution of 2C, and for the perpendicular component, you just have to apply the solution of 2B. Okay, so with that, you can basically just write down the solution. So first of all, the very first contribution is the contribution of the dipole itself. So this one is the contribution of the dipole P. And then for the horizontal component, for the parallel component, we can just use the solution of 2c and replacing all the p with p cosine theta. So we have the image charge again r over d to the power cube, r minus r square over d and also we have the monopole moments contribution. So this you can refer to question 2c. And for the perpendicular component, we have this form, just the image dipole only. So you can refer to question 2b. And that is the solution. Oh, not yet, because you should also consider the potential inside the sphere. So of course, the potential inside the sphere is always 0. And that is the solution of question 2D. Okay, so that's the end of today's exercise class. Thank you for your attention. So if you have any questions, you can just email me or post a question on Blackboard. So that's the end. Thank you very much.